And now, please welcome Ian Beer.
Hi, everyone. Thanks for coming. This is my first time at Black Hat, and I'm staying here at Mandalay Bay. So I don't know if anyone else got this on their door this morning. Like when I woke up very early, very jet lagged, and like opened my door, there was this thing stuck on there. This has got nothing to do with Apple, by the way. This is just an observation. And so anyway, like open up this box. I was like, oh, maybe it's some lovely chocolates that I'm definitely not going to eat. What's inside here? Oh, it's like some. So on the front, it's some like cyber startup thing. If you work here, if you work for them and you're here, hello. I don't really know what it does. Something cyber. Anyway, you look at this thing, morning recovery. And if you actually read what's on the back of this thing, I mean, what's it saying there? That this theory of thing is here to help you feel better after a night of celebrating. Oh, and by the way, this statement has not been evaluated by the Food and Drug Administration. So it seems to me like a very bold strategy to market your cybersecurity company with a product that the FDA is declaring snake oil. Yeah, so I mean, anyway, I don't know who thought that was a good idea. So anyway, let's get back to the real talk. So my name's Ian. I joined Chrome Security in 2013 and then moved to Project Zero when Chris Evans started this team. So we have an expanded remit to look at the security of the internet. And so my personal focus has mostly been on iOS, and these days with a major focus on sandboxing and kernel exploitation. Why should you listen to what I have to say? So I think I have a pretty good idea how iOS actually works and how to exploit it. Yes, my exploits are not perfect, but nevertheless. And since Apple launched their bug bounty a couple of years ago, I've spent a lot of my time writing exploits for iOS to make it easier for researchers like you to actually be able to participate in that bug bounty. If you've SSH'd into an iPhone in the last 2 years, you were probably either using your own exploits or potentially ran one of my kernel sandbox exploits. So actually the main emphasis of this talk today is to talk about why I think this stuff is important and why I don't think vendors are taking exploitation seriously enough. I think this is something that we as Project Zero maybe don't do such a good job of. So we're going to start with a history lesson. Yes, this is half my lifetime ago, but like I think it was formative stuff. It was in the news all the time, right? And what kind of things were in the news all the time? This. This is a diagram from an IEEE paper about Slammer. And if you were at Black Hat 15 years ago, you could have seen them put on stage the code that was this. What actually was this? This is a strict copy from the first byte of a UDP packet onto a 16-byte stack buffer, right? So this is some Microsoft SQL Server code, and it's expecting that the UDP packet has a null-terminated database name as like right at the beginning of the packet. And so the server is trusting this. Why am I saying this? So what did things look like 15 years ago? Poor security development practices used to lead to clearly visible harm. And people cared, right? Specifically, Microsoft's customers cared. And they were really worried about the future. And so, I'm sure you're also all very familiar with this. This caused Bill Gates to write this famous trustworthy computing memo. And yes, I'm going to read it off of the screen. Not all of it. Our new design approaches need to dramatically reduce the number of such issues that come up in the software that Microsoft, its partners, and its customers create. It goes on. At the same time, we're in the process of training all our developers in the latest secure coding techniques. Now, I've actually managed to grab hold of some of those internal training materials from Microsoft at the time. This is one of their motivational posters explaining about the dangers of strict copy. Thank you to Natashenka for getting hold of this for me. So one last quote, and this is from Bill Gates. So now, when we face a choice between adding features and resolving security issues, we need to choose security, right? And this memo was the foundation of Microsoft's secure development lifecycle 15 years ago. So 15 years later now, surely everyone now develops secure systems, uses safe languages, and if they must write low-level code, they use annotations and model checking to help those developers. And in some products, Microsoft is on their way down that path. But did everyone take that route? And what does the world look like today? So now in this mobile-first world, Microsoft is not such a dominant player on those mobile endpoints, right? It's now Android and it's now iOS. And these code bases in their current forms, they didn't exist then. Yes, XNU did exist 15 years ago. It did exist almost, not XNU, but large parts of that code base existed 30 years ago. But the security models of iOS are vastly different from the security models of XNU and Mach. And these code bases never went through this sudden moment of clarity that code quality, like not strict copying to the stack, is actually super important. So what are the consequences of these code bases never having gone through such an event? Well, it doesn't look like a big map with blinky lights on it. Instead, it looks like these two 42U racks, also with blinky lights on them. So maybe some of you are familiar with where this rack diagram is taken from. So this is from the Pegasus product description manual. It was leaked during the hacking team attack. And why am I showing you this? So most of the discussion you read about NSO and about Pegasus, they generally talk about numbers. They talk about numbers and exploits. And you can see the talks about Pegasus from the team at Lookout who reversed the exploit. It was like super good, super excellent write-up. And I'm sure you've all seen like the stories that came out of this in Wired, like these $1 million dissident story. And that's what people take away. I think that to take these big numbers, like $1 million, as kind of a comfort blanket. I'm pretty sure that like Google directors do this as well. I think the reasoning goes, well, you know, $1 million is a lot of money, right? To hack one person, ASLR works and makes us 99.7% secure. And what I want to try to paint with things like this is a different picture. So Pegasus is a product from NSO. Let's all not forget that NSO is a proud American company. Yes, they're 70% owned by San Francisco private equity. And what are they selling? They're not selling exploits. They're selling complete computer network exploitation in a box setups, right? In these two boxes. And in addition to this, you also get some like Windows boxes that run their front end, like data visualize. Someone's just moving their Pegasus installation. So there are two motivational points I want to emphasize here. Firstly, this massive 2 rack installations is clearly targeted at customers without CNE experience, without computer network exploitation experience. Like the manual that this is part of explicitly states that for their over-the-air installation method, the operator only needs to put in a phone number and the agent is installed, right? There's no more details. That's the level of sophistication which they're expecting from their customer. So my personal fear here is that exploitation, using things like this, is an extremely powerful and asymmetric tool. And you and maybe I, and probably I, might feel comfortable that some government institutions in some governments in the world are capable of handling such tools, but this product is not targeted at them. This is for organizations and for countries rather that don't have decades of experience in the technical and policy discussions that are required to like balance the use of this power. And in the wrong hands, this is a very, very powerful weapon against things like dissent, which is how it's used. But it's not only used for suppressing political dissent. You know, the slippery slope of the use of tools like this is real. So one global problem which products like this contribute to is obesity, right? Especially in the US and all across the world. So Citizen Lab, this group from Canada, have collected evidence suggesting that exploits served by one of these installations were sent to employees of an NGO in Mexico that campaign in favor of a Mexican soda tax, right? Is that really a justified use of this kind of power? The second point I want to make regarding this is that these prices, which you hear quoted everywhere, I think are widely misused to paint an inaccurate picture of code quality. This comfort blanket of like, okay, maybe the code isn't perfect, but it's still like $1 million to exploit someone. This is not real and it's really not helpful. This system is not serving a unique single exploit per target. right? The true discovery and exploitation costs of the bugs involved here, I think, are far lower than people believe. And this is the area that Project Zero are focused on. So you've got to remember these quoted prices are taking you from literally nothing to this kind of mid-level intelligence agency capability. That costs money. And most of that money is not the cost of the exploits. So what does the world look like now? 15 years later, now, poor software development practices lead to hidden harm. With some squiggly arrows, poor software development practices in Android and iOS lead to hidden, but quite widespread and damaging, but easy to ignore harm. You know, these are different code bases that are under attack now, and they never had this slammer moment. Their development practices were never forced to mature, and for them, in feature versus security, feature seems to always win. So in the rest of this talk, I'm going to try to convince you of just how poor those practices are. And yes, I know more stuff about iOS than Android because that's just happens to be what I work on. Please go read the Project Zero tracker, read the report from the bug that Jan released on Monday if you think Android's any better than this. So stuff has changed in the last 15 years, right? It's unlikely, I hope, that Pegasus, a Pegasus payload sends a single UDP packet, unless it's targeting Internet of Things. Or any embedded chip on your phone, right? Like the Broadcom Wi-Fi chip. Maybe there it's sending one packet. But we have things like sandboxing, which mean that you might need more than that one bug. What's my provocative statement here? Security systems design is making promises which poor software development practices cannot keep. And when I'm talking about things like sandboxing, what I'm talking about are the implementation details of sandboxing. Now, it's more likely nowadays that the thing you're served by Pegasus is like a small chain of bugs. But that doesn't necessarily mean that those bugs are all that hard to find or all that hard to exploit. So I'm going to focus a bit more on this systems design stuff, because I think it's important to understand how these companies think about secure software development. So if you search around hard enough on the Apple website, you'll come across this diagram. It doesn't matter too much what's on there, but this is from the iOS security white paper. And it's got this layered diagram of data protection class, app sandbox, user partition, encrypted, OS partition. So both iOS and Android's current security leads come from these security systems design backgrounds. So on the Android side, it's now the security lead is Dave Kleidermacher, has a background in doing small real-time OSs in avionics. So it's possible that the plane that you flew here on was running some ARDA code that ran on his OS from 20 years ago, right? Ivan Kristic on the Apple side, prior to Apple, was at OLPC, this one laptop per child thing. And Ivan, I bought one of those back in the day. And so there he led their security architecture. It's called Bitfrost if you want to go see. Look it up. So undeniably, both these security leaders have really strong security engineering skill sets, but they don't come from an exploitation background. So this academic understanding of security perhaps tends to kind of discount implementation flaws. If a bug's found, you fix it, and then the system's perfect again. And the focus is on the design of the system and not the implementation. You can go watch Ivan's talk from 2 years ago at Black Hat to see examples of this. So I don't come from this background. I come from an exploitation background, and I see things the other way up. So to me, code is nothing but a collection of bugs in implementation details. And so what's my opinion of security systems design? Yes, again, this is another deliberately provocative statement. Given sufficient bug density, security design is irrelevant. So everything that I'm saying kind of goes against the little which Apple publicly say about bugs in iOS. So there is very little you can find out there. So this is again from Ivan's talk 2 years ago. And let's read the quote from the screen. So feedback that we've heard pretty consistently, both from my red team at Apple, I hope some of them are here today, and also from researchers directly. I don't know what weird actual security researchers hacking iOS are telling Ivan that it's hard. Maybe you shouldn't trust them. But these people are telling us that it's getting increasingly more difficult to find I've typed this wrong, to find some of those most critical types of security vulnerabilities. And so I'm putting it to you that everyone is wearing this comfort blanket of like thinking that this is hard. And I'm not trying to say it's not hard. What I'm more trying to emphasize is that I don't think that many people are actually looking. And it's as simple as like, if you don't look, you definitely won't find anything. And it seems to me to be much more a factor of time you put in, and I put a lot of time in, like this is all I do, equals bugs out. So right, let's actually like get to some bugs. Yes, for those of you from Apple, this is a very old example, but I will get to some much more relevant examples, or some much more recent examples. But I think nevertheless that this is, like the lessons that you can learn from this example do still apply, right? So when Ivan was making this point, that it's getting increasingly difficult to find more of these most critical types of security vulnerabilities, this code hit one of the iOS 10 betas. And it shipped first in iOS 10, which was the first iOS release which qualified for the Apple bug bounty. So if you're not familiar with the XNU kernel, this is a brand new syscall, reachable from any sandboxed context. Like the sandbox is not involved at all here. So for example, you can reach this from the Safari renderer. So it's fun to like play spot the bug here. So I'll just like tell you a little bit about the APIs in case you're not familiar with them. So copy in, let's have a look. Copy in is like a copy from user on Linux. So the first argument is a user space pointer, second argument is a kernel space pointer, and the last argument is the size. I'll just have some more Pepsi, and you can look at the code. Because this is an example of a bug that it's actually kind of fun. It was kind of fun at the time to show people in the office because it really makes you do a double take of like, is there actually a bug here? So right, let's walk through the code. So what are we doing? We're going to copy in. So args points to stuff that we control from user space. So we're going to copy in from recipe size, user space pointer, to sc, this size, the size of size. All right, so easy. So recipe size points to a size. And then we pass that size to calloc, which is like the kernel space general purpose heap allocator. And then we get back this chunk of memory, k recipe. And later on down the bottom, we're going to copy in from args recipe, pointing to some kind of recipe structure. It doesn't really matter what recipe is, to k recipe. And how much are we going to copy? We're going to copy recipe size. Oh, that sounds fine, right? We're going to copy the size. Except wait, hang about. If you go back up to the top, recipe size was used as a pointer. And now it's used as a length. So like, this code shipped for 6 months until I got around to grepping the XNU diffs for copy in, because yes, that's what I do every time these diffs come out, like very sporadically. So this is the kind of issue that I'm claiming is still on the same order of like complexity as David Litchfield's SQL Server bug from 15 years ago, right? For this kind of issue, there's no need to understand like complex or esoteric stuff about the operating system. Just knowing C should let you see that this code is completely wrong. So clearly there are no annotations. There's nothing like Linux is __ user. Actually, you probably get some compiler warnings. But I don't know if any of you have ever tried to compile XNU with all warnings enabled. Yeah, good luck reading through that and finding this. So what are my main points here? Well, what about code review? I'm not blaming the individual developer. In fact, if you look at this code, you can see why it ended up like this. This is just copy and pasted from some other code, and they made a subtle change to the API. Writing C code is hard, and this is a new syscall reachable from everywhere on the system, and it has clearly not been reviewed by someone with a vulnerability research background, because they would spot this. And yes, this example is from iOS 10. This kind of stuff is still happening today in iOS 11, and the motivating examples are so motivating and recent that I can't talk about them because they're still under the 90-day deadline. So, right, what about testing? Right, you might realize it's actually kind of tricky to make that code run. It's actually kind of tricky even to exploit this code because it will just kernel panic. So yeah, there are no tests, and there's also clearly no fuzzing. All right, so maybe everything's better now, right? So this is an example from the exploit I released a month ago or so called multipath. And so we'll just do one more spot the bug in some C code. So this feature is called multipath TCP. It lets you take a TCP and like run it over multiple multiple network interfaces. So if you want to play spot the bug, you control what dest points to. It points to one of these sock adder structures, like the POSIX sock adder thing. And so if we just look through the logic of this code, I've commented out a bit, but the logic is still the same. Right, so if this sock adder is AF INET, so IPv4 socket, and the length is not the size of an IPv4 address, then we bail. If the family type is IPv6 address, and the socket length is not the size of an IPv6 socket address, then we bail. Otherwise, if we have some other if, which has got nothing to do with the length, then we just like memcopy straight into here. So you control SALen, it's a single byte, so it's up to 255 bytes. And you can go read the Keen team write-up for my exploit for this. It's actually exploitable in kind of an interesting way because you can overwrite interesting pointers inside this structure. You don't really need to do any heap grooming to get a use of a control pointer here. So yeah, those two bugs lie firmly in this class of like legacy bugs. I mean, they're not legacy bugs. They're not 30-year-old Mach bugs. They're very new bugs. But they're this class of like legacy C coding problems, right? Which maybe we shouldn't have anymore, but we definitely do. So again, please, like, I'm not trying to criticize the individual developers who wrote those two particular examples. These are failures of process. It shouldn't be possible to commit this kind of code, right? It should be prevented by annotations. It should be prevented by code review. It should be prevented by manual testing. It should be prevented by fuzzing. And this is the kind of stuff that Bill Gates was talking about 15 years ago, right? And this should not be happening in quote unquote secure code bases now. And in case you think I'm just taking two examples, like please go look at the Project Zero bug tracker and see all of the similar issues, right? My point is that this is systemic process failures, and that's what Apple need to address. So there are other classes of issues, which are perhaps more interesting than these C bugs, which fall into more like this bucket of more esoteric issues. So they're not just simple C coding problems, like buffer overflows like these, but they require kind of more understanding of the underlying system and its paradigms. So let's take a look at two examples of esoteric bugs, which also say something about Apple's security culture. So I don't know if you've read this book. This is a book from 2012 by Jonathan Levin. And so iOS is based on this combination of BSD and Mach. So Mach is full of like a bunch of really weird APIs. And like Apple are slowly turning these APIs off, removing them, and this is a very good thing. But I definitely get the feeling that Apple lacks the kind of institutional memory to know why many of these things are there or are still there. So I think I mentioned before that iOS has a very confusing and complicated privilege model, right? It's way more complicated than just user and root. Root is completely distinct from kernel code execution on iOS, and each process has its own set of these things called entitlements. And checks for these entitlements are like dotted basically seemingly randomly across user space and the kernel. So what is this bug that's in this book from 2012? So this is some old feature from Mach that if your root gives you read-write access to all user space processes on the system, read-write access to their memory, without requiring the entitlement that's meant to stop you ever getting that. Right, so I didn't find this bug. It's in this book from 2012, right? And obviously when I read this, I just kind of assumed it had been fixed because, you know, it's in this old book. But, you know, I found myself in the situation with a bug where I was able to test this, right? So if you just go buy a device from Apple and test this, you can't because you need to exploit some ODE that you found that's not patched in order to get root, in order to copy paste. But you don't even need to type the code in from here because Jonathan Levin even put it on his website with a big like banner saying this is a bug, right? And it only got fixed after I used it in an exploit. So what's my point here? Apple are clearly not doing enough proactive vulnerability research, and they're not even fixing these bugs that are documented in books. Right. So I've discussed lack of code review, lack of testing, auditing, and proactive vulnerability research. I felt obliged to have at least one slide with some assembly in. So what is this bug? This is an example of a failure of variant analysis. So in 2016, I reported a bunch of issues I found in these user space services, which are written using this ancient tool called MIG. And I feel obliged to show you some MIG code. This is the Mach interface generator. It's literally thousands upon thousands of lines of C code, fprintfing more C code to generate these handlers, right? And these are used everywhere. This gets you from the user to kernel or between all of these user space processors. So much of it is built on this literally impossible to audit code base. But this is not about bugs in that code generator. It's about a much simpler aspect of MIG, which is this simple rule for object lifetime management. So for the objects that you pass across an RPC boundary, there's a simple rule. If your handler returns 0, which is a success value, then your handler is responsible for the lifetime of any objects which will pass to it. And if your handler returns an error code, you are not responsible for the ownership. Namely, the system, the RPC system, is responsible for the ownership. So this leads to a very common class of bug, which is if you have a handler which takes ownership of a reference, in this case, it is dropping a reference on this object, and then W22 ends up being the return value in X0 for this method. What that means is that the actual MIG system itself will decide that, okay, the code didn't take ownership of this object, so I'm going to release the reference. And this leads to, in this case, dropping a reference that was only taken once and dropping it twice. So I reported the first instance of this in 2016. You can go into the Project Zero tracker and see where I quite explicitly say there are more instances of this bug. And it's really hard when you only have the binaries, which is what I have for almost all of this stuff, unless it's on opensource.apple.com. It's really hard to go find all instances of this. But in the source, my guess is that it shouldn't be so hard, right? But I see very little evidence. Again, very little evidence up until like bugs that I can't show you. That not enough variant analysis of things like this are happening. For example, one of the Keen team bugs, which they are nominated for a pony for, is this bug class, which I pointed out 2 years ago. So yeah, what I'm trying to tell you is that this is like systemic, and these are avoidable. And yes, let's skip ahead past that. So I've spoken a lot about what I think Apple are not doing. What are they doing? So if you prefer to try to engineer your way out of things, rather than investing in proactive vulnerability research and developer process changes, then you write mitigations, right? And this is a trend across the whole industry. Android and iOS are like especially invested in this. So you can watch Dave Kleidermacher's talk from the Google Cloud conference a few weeks ago, explicitly saying this, that Android's mitigations are the things that make it more secure. And in my opinion, this is like dangerously naive. But these people don't come from an exploitation background, and so it's hard for them to weigh up the true impact or lack thereof in these mitigations. In fact, I also often get the feeling that the people designing and implementing these mitigations don't necessarily have exploitation backgrounds either. Often it's more the case, and especially you see this in iOS, of there was a public proof of concept exploit or an exploit in a jailbreak. Let's make a small change to how the heap allocator works, and now the POC doesn't work. We're done, right? So Halvar Flake, who works with us on Project Zero, has been making this point a bunch recently. You can go watch his talks about this. Yes, again, it's like deliberately provocative. I don't think weak mitigations are that bad, but weak mitigations can be trivially defeated with more bugs. And if you don't care about bugs, there's no point in shipping these weak mitigations. So what is the canonical weak mitigation that everyone implements? Randomization. So I'm only going to talk very, very briefly about randomization. Go read all of Stefan Esser's talks about iOS exploitation. And he covers like the whole history of iOS kernel heap exploitation and how it's changed over the years. We'll just look at like this one tiny aspect. So this is the iOS kernel heap. It's one small part of the iOS kernel heap. So you have this thing called the zone map. This is a 384 megabyte region of kernel vector address space. Yes, regardless of whether you bought a $200 iPod Touch or a I don't even know how much it costs, $1,800 iPhone X with 3 gigs of RAM, you don't get a bigger kernel zone heap, sorry. You only get 384 megabytes. So this thing is a pool allocator, and that 384 megabytes gets split up on demand into smaller regions of like a few pages. And then the zone is like keeping track of individual allocations inside there, and if the whole region is free, then this smaller region is a candidate for getting given back to the underlying system if there's memory pressure. So we saw the call to calloc earlier. So calloc underneath has its own bunch of zones for different sizes. If your calloc allocation is bigger than a certain threshold, it doesn't go to the zone map, it goes to the kernel map. So a recent mitigation, I'm not too sure when this was introduced, maybe sometime in iOS 10, was to add some randomness to the initial state of this free list. So it used to be allocated like this. So this is actually linear. Actually, when I say it used to be allocated like this means that when you actually make a calloc, and then the next calloc, and then the next calloc, it comes backwards. So it's just pushed onto the free list in the other way around. And so this recent mitigation, rather than making it go like that, now it goes like this. So it randomly goes from the inside to the outside. So this is the world's most useless bug. I only found this because there was a bug in my heap groom, and I became convinced that the random number generator they had must be like totally broken because it didn't look random at all. So I was like, right, let's look at the random number generator. Actually, this random number generator is slightly broken, but it was just a bug in my code. I think this has absolutely no security impact unless the people from Apple tell me that actually they also use this for their like VPN, but probably not. So what's this actually trying to do? This is just some trivia. This is taking an actual random number generator and trying to generate a random bit stream. I think we probably do have enough time to just quickly walk through this code because it's kind of interesting. And like, I am no cryptographer, but even I can spot that this thing is kind of biased. Right, so what's it doing? So it comes in with this buffer and count. So buffer points to count number of uint32, so 32 byte D words. Right, find a portion of the buffer that hasn't been emptied. We might have emptied our last index in the previous iteration. So it's originally this index value is 0, and then it's walking through each of the D words, trying to find the first one, which is non-zero. Right? And if the first one that's non-zero, or if we didn't find one that was non-zero and we got to the end, then refill the buffer. Then collect a bit. So what's that doing? You can practice your bit twiddling. It's pulling the least significant bit from the D word at offset index in buffer, pulling that out into bit. It's then shifting that value in buffer down by 1, so it's shifting the bits down. And then it's ORing that bit into the result bits. And it goes back around again. And this thing is re-entrant, so in the sense of that same buffer will get used again. So what's wrong with this? If this was actually like cryptographic? This like weird way that they are like checking if the value has been complete, the D word has been consumed by seeing if it's equal to 0. So this misses out leading 0 bits in those random D words. So actually the bias you get from it is like totally meaningless for, so sorry for wasting your time. It's totally meaningless for heap randomization, but nevertheless. That's the only ODA you get in this talk, sorry. Right, but back to using this ever so slightly biased random number generator for kernel heap allocation. Like, what effect does this actually have? So if you look at it from an exploiter's perspective, especially from an exploiter's perspective who knows that bugs are dense and you have a choice of bugs, well, what's the first observation? There's still a pattern. right? The pattern is no longer linear, but there is a pattern still there, and there's still stuff we can do with that pattern. So one example of an operation that I've used with precisely this pattern in the empty list exploit, you can go read a write-up of this, is to reverse the order of this free list. So rather than your allocations going from the inside out, they go from the outside in. And this has some properties that in the case of the empty list exploit were useful. And this doesn't require like a new bug, right? This just means finding the right primitive. In this case, it's very easy, right? You just allocate a bunch of objects and then find some, and then free them in the same order. And this swaps the free list around. The second observation here, larger objects are less randomized. So the randomization only applies to this initial free list population. And generally, like the bigger your object, the shorter the initial free list is. And yes, at the limit, the initial free list is of size 1. So it still calls the random number generator, but it generates a single random value that does, yeah. So I exploited both of these things. So I exploited this part 1, that there is still a pattern in empty list, and in extra recipe, which is my exploit for that first chunk of code that I showed you, I used this property that actually I was able to control the size of the object that was overflown out of, which means I could just choose the size that doesn't have this randomization property. Third thing, can we just sort the free list, right? Again, this doesn't necessarily need a bug, right? You've just got to find some optimized kernel data structure, like a hash table, that has some primitive that is going to like sort on the addresses of objects. I don't have an example of this to show you, but just to like emphasize the point that it's not so simple to actually guarantee that these mitigations have any impact at all. So yeah, some more provocative statements. Please stop just spot fixing bugs, learn from them, and act on that. So this current fashion, which we see all over the place, that mitigations will save us, mitigations will not save you. Strong mitigations, which is like making real meaningful reductions in reachable attack surface, are relevant in combination with caring about bugs, right? Each bug needs to be a lesson. If this is truly a secure code base, then you need for each issue to be like, why is this here? How was it introduced? How could we have caught this earlier? Which process problems do we need to address in order so that we could have caught this earlier? Who should have had access to this code to review it, but for whatever internal or political reasons didn't have that access? How do we find every instance of this bug and fix it? How do we genuinely kill this class of bugs? So the attitude that I would love people to view these bugs through, or the lens I would like them to view these bugs, is someone has already found this issue. And like, I can't talk on the stage of Black Hat about things like suspected bug collisions and who I think they collided with, but I think these issues collide with people. In fact, I'm very certain that a large proportion of the issues which I've reported in iOS have at some point been actively exploited. In fact, the thing that worries me more, and over which I have even less control, is that trivial variants of the things that I have found and reported are still being exploited in the wild. And that's why I want to do this Apple one more thing. So the reason I decided to give this talk is that I think I'm failing in my goal to do, my small part to move the world towards this vision of trustworthy computing. It's way too easy for vendors like Google and Samsung and Apple to ignore exploitation. One of the problems here is that they like to tout themselves as being data-driven, right? Making decisions on evidence and big data. And this doesn't work for this kind of security. By definition, good attackers don't get caught. You don't collect your big data. And I hope that I have kind of managed to convince you that maybe targeted exploitation is actually kind of widespread, and more importantly, is too easily abused for causes which you probably don't believe in, like stopping people drinking this. It has a societal impact, and that societal impact is much wider than the single user who is targeted by each attack. And I hope I've also kind of managed to convince you that the bar for iOS exploitation is kind of lower than you probably think. There is no comfort blanket that you can wrap yourself in to think that just because you're campaigning for human rights or against childhood obesity, that you're not a target. Yeah, I've had to leave out a bunch of anecdotes which would make these points more clearly, because I am, for some of the anecdotes, afraid of being targeted, and not by governments, but by private individuals who also are part of this. I rely on this device. But yeah, nothing really changes. Like Parissa said in her keynote this morning, it's all spot fixes and not raising the bar. And without this kind of organizational change from the top, declaring that all of these vendors, Apple included, have a security problem, nothing is going to get better. So I've reported over 150 bugs, similar to those handful that I've shown you today, all with detailed technical write-ups, and I'm still not seeing any momentum within Apple for genuine process change from the top. So let's end with one more example of why the stuff still matters. So this is a report from last week from Amnesty International, this global human rights organization, and their employees in Saudi Arabia were targeted, or suspected of being targeted, by a user of one of these Pegasus installations. And if you read this article more closely, and you look at the screenshots, well, you'll notice that those screenshots are from the iOS messaging app, right? They're using iPhones. This stuff is real, right? This is happening. And it's way too easy to ignore. So yes, we have made some progress, like Parissa said. So maybe now Apple don't take over a year to fix most externally reported bugs, but I want more than that. Yeah, so I want to see real organizational and process changes, and not just spot fixes anymore. And just sending these hundreds of highly technical write-ups and bugs has not achieved that. So I am going to try something else. So 2 years ago on this stage, Apple announced that they were starting a bug bounty. And here are some quotes from Ivan's talk. It's not meant to be any kind of exclusive club. So if anyone who is not in the program brings to us a vulnerability that would be covered under the program, we welcome that. We're going to take a look, and if the work merits it, we'll invite them into the program and we'll reward the vulnerability that they found. So I don't think that Apple ever intended this bug bounty program to be a PR tool. I mean, obviously it's given them lots of good PR. It's again got these numbers out that people use as these comfort blankets. But I think that Apple do on some level genuinely care about getting more security bugs. So there was one other thing they said. So in addition to these exact amounts, we will let researchers donate the reward to a charity of their choosing. We will, at our option, match that one-to-one, doubling the donation. And so it might surprise you to learn that I and Project Zero have never been invited to be part of this, even though we would absolutely love for Apple to donate the bounties that we find to charity. And so that is what I'm asking Apple to do today. So here's 30 bugs I found and reported to Apple. So I think every one of these met the bar. They all have detailed technical write-ups, repo cases, and they each defeat a critical part of the iOS security model. So yeah, if you add it up with the corporate donation matching, it's $2.45 million. And so yeah, Apple, today I'm asking you to follow through on that bug bounty you launched 2 years ago. And I have one thing to say directly to Tim Cook. Where's the camera there? So Tim, I'm really worried that people are getting hacked using variants of the bugs that I report, and you do a poor job of fixing. So some of these issues are highlighted. In fact, those are the ones that aren't fixed yet. Please go look those up in your bug tracker and find out why they happened, why they weren't caught earlier, and what processes need to change to prevent them happening again. And I'm very happy to sit down with you with my laptop and walk through these issues, and together we can make things better. And so just to make sure Tim finds this out. So I don't have Tim Cook's email, but what I do have, I can is, oh, it's very small. What's the wrong one? Oh no, my trash. What I do have is an inexplicable number of Twitter followers. So I'm just going to tweet to Tim now, just so he sees this with that picture. There we go. You can see all the interesting things in my Twitter feed. So yeah, thank you for listening, and